Hi everyone, welcome to EZAphysics. Today we're going to be looking at our first video, which is based on kinematics. This is the first video of a multi-series video that I'll be making for Physics 1. So let's take a look. So kinematics. What is kinematics? Kinematics is the study of motion without reference to forces in play. So basically, the variables we consider are displacement, distance, acceleration, velocity, speed, and time. So let's define some of these terms. So acceleration is the change in velocity over time. Speed is the rate of change in distance. And velocity is speed in a given direction, or it can also be the displacement over time. So rate of change in displacement. And displacement is how far an object travels from the starting point. And the distance is the total path length traveled. So we'll be taking a closer look at these when I do some example problems later on in the video. And yeah, let's move on to scalars and vectors. So a scalar is a measured value that only has a magnitude with no direction. So speed and distance are your most common scalars that I'll be taking a look in kinematics. And on the other hand, we have vectors. Vectors have both a magnitude and a direction. And direction can be represented with like north, south, east, west, positive or negative, all those things. And then you have velocity and displacement are the two key vectors, as well as acceleration. Let me add that. And okay, so that's it for scalars and vectors. So now let's take a look at some graphs. So when we look at kinematics, we analyze three graphs: position versus time, velocity versus time, and acceleration versus time. So right here we have a position versus time graph. So a position versus time graph shows us the relative location or point an object is located at a given time. And from this graph, we can just find a lot of information. So we can find the velocity at a specific time on the graph by determining the slope. And there are many different types of slopes, right? We have a linear slope here. We have a curved slope here. So if you see a curved slope, like we see here from 0 to 4, that indicates that there's an acceleration. However, if you just have a linear slope, like shown from 4 to 5, that indicates that velocity is constant and there is zero acceleration. And also, if you just have a horizontal trend, that indicates that there is no velocity since the position is just staying the same, and that also has to mean that there's no acceleration. Yeah, that's about it for position versus time graphs. So let's move on to velocity versus time graphs. Okay, so the velocity versus time graph shows us the velocity at a specific time interval, and the slope of a velocity versus time graph, that gives us the value of acceleration. So the slope of this graph is 1, if you just count rise over run. So in this example, the acceleration would be 1 meters per second squared. And something interesting about this is that the area under the curve can give us the value of displacement. It can give us the displacement of an object at a specific time interval. So if we were to find the displacement from t equals 0 to t equals 2 from this example, we'd calculate the area from that time interval. So that would be 1/2 the base times height. So 2 times 2 is 4, divided by 2 is 2. So displacement will be 2. And if we were doing it from 0 to 5 seconds, the displacement will be 5 times 5, 25, divided by 2, which is 12.5 meters. So that's how you can find displacement using a velocity versus time graph. And something to note is that when the line crosses the x-intercept, that indicates that the object changes directions. It changes direction that it's traveling, because on this axis here, this is the positive axis. And then if it goes below the x-axis, so you can't really see it from this graph, but if it goes below, like somewhere here maybe, like around this area where it's negative, the velocity becomes negative, so that means it also changes direction. And something else to note is that at t equals 0, if your time interval starts at t equals 0, which is for almost all problems, the y-intercept indicates your initial velocity. And also one more thing. So when you calculate the displacement in the positive direction, that can also equal distance. So when the slope goes to the negative direction, so when it goes past the x-axis and below it, basically you're getting an area under the curve, under the x-axis. And if you're calculating displacement, you want to subtract the area you get under the curve from the positive area you get above the x-axis here. But if you were to calculate distance, you would simply add both the areas. You would add the area above the x-axis and the area below the x-axis. And that's about it for a velocity versus time graph. So let's take a look at some key differences between velocity and speed. So velocity is basically just speed in a given direction, a vector, and speed is just a distance over time. So when we do when we're going to go into our examples, um, we'll show that like the average velocity and average speed, they're not always the same values. So yeah, so let's move on to an acceleration versus time graph. So an acceleration versus time graph just shows us the acceleration of an object over time. So a slope of 0 on this graph indicates that there's constant acceleration. However, if we had like some increasing slope, that would obviously mean that acceleration is changing at a rate. And the area under the acceleration versus time graph, similar to a velocity versus time graph, it'll give us the velocity. So the area under this graph from t equals 0 to t equals 6 would give us the velocity, which would be 12 meters per second. And yeah, that's about it for acceleration versus time graphs. So now let's look at some key equations for kinematics. So here's the first equation. This equation shows the displacement equals the initial velocity, so the starting velocity at like whatever starting time interval you are at, times the time, plus 1/2 times the acceleration, times the time squared. And then our next equation we have for acceleration, which is equal to the final velocity minus initial velocity over time. And through plugging in this acceleration equation, we can also just derive that the final velocity is equal to the final velocity squared is equal to initial velocity plus 2 times the acceleration times the displacement. And something to just keep in mind, displacement is not always just delta x. If you're finding displacement in the y direction, you can use delta y. It's just like a representation. And okay, so our next equation is speed equals distance over time. This is pretty straightforward. You find the distance and just divide by time. And then average velocity is the displacement over time. And in some cases, it can also be the final velocity plus the initial velocity divided by 2. However, this only works under uniform acceleration or when the object traveling at an initial velocity and final velocity for the same amount of time. So yeah, that's about it for the equations we'll be using for kinematics. So now let's look at some vector components. So breaking a vector up into its components is going to be very important for some questions we do later on. So keep in mind that the x and y direction, they act independently of each other. So what this means is that in the x and y direction, they'll have their own individual velocities, accelerations, and displacements. They can have their own independent variables for those. And then for some questions, you'll have to break up the vector into its x and y components. So let's take this diagram for example. If we have a vector v going at an angle theta, how we would find its components. So the vertical direction, the vertical component here, we would find that using v sine theta, the hypotenuse times the sine of the angle. And for the x component, we would use v cosine theta, the magnitude of the vector v times the cosine of the angle. And if it was like reversed when we had to find the angle and we were given the components of x, y, or maybe the v, we could use these three equations. We can use theta equals the sine inverse of v y, that should be y, but vy over v, or we could use theta equals the cos inverse of vx, over v. And lastly, we can use theta equals the tan inverse of vy over vx. And yeah, so that's about it for like the basics of breaking a vector into its components. When we do more example problems later on, um, you'll understand how we can use these in a more complex way. And these are some example problems. Okay, the last thing I want to cover is projectile motions. So projectile motion is when an object is launched in the air or released from rest. It's free falling under the influence of gravity. So there are two types of projectile motions, 1D and 2D. 1D is just when an object is launched vertically or free fall vertically at rest. It's going in one dimension, which is vertically. And then we have 2D, which refers to free falling motion when there's both a vertical and horizontal velocity. So this can happen when objects launched at an angle from the ground or just released with initial horizontal velocity and then it starts falling under the influence of gravity. And when an object falls under the influence of gravity, it has a gravitational acceleration vertically. This only applies to the vertical component of negative 9.8 meters per second. However, when we have 2D projectile motions and there's a horizontal velocity, we neglect what is known as air resistance, which is just forces caused by the air to influence its acceleration. So we ignore that when we're looking at kinematics, and this also means that the acceleration is zero, which means the horizontal velocity always remains constant. So yeah, let's take a look at a projectile motion chart, and it will make much more sense, hopefully. So if we take a look at this chart, right, we see that like a ball is launched with a velocity v. So we can break it up into its components, vx, vy. So vx will be v cos theta, and vy will be v sine theta. So when it's launched, it keeps traveling upwards, upwards, upwards until it reaches a maximum height. At this maximum height, the vertical component of velocity equals zero because the acceleration is traveling in the opposite direction of the initial vertical component, since the vertical component is going up and gravitational acceleration always goes downwards. So it keeps traveling upwards until it hits a maximum height of zero, and then the vertical component starts to travel in the downwards in the negative direction because of gravitational acceleration until it reaches the ground here. So throughout this whole trajectory, if the object starts at the ground and it lands at the ground, there are a couple of things we can keep in mind. So if this is true, then the time it takes to reach the maximum height will be equal to the time it takes to reach the ground from the maximum height. So from here, t equals 0 to t equals something, that time interval will be the same as from here, the time here, to the time it takes to reach the ground. Okay, and that's basically what we gotta know so far. And one more thing, so when it travels from its initial starting point, the ground, travels all the way, reaches the ground. From that point, the vertical displacement will always be zero if it reaches the same place it initially started with. And also the initial velocity it was launched with, it will be the same as the final velocity as it is about to touch the ground. So if it was launched with if a ball was launched from here at with a velocity of 5 meters per second, it's gonna reach the ground right before it touches the ground. As it touches the ground, it's gonna also land with a velocity of 5 meters per second. And yeah, that's basically what we gotta know for projectile motions. Now we'll be taking a look at some example problems. Let's take a look at some practice problems. And keep in mind that these questions are not too conceptual. They're not too difficult. The point of them is just to establish a basic understanding. I'll be making another video where I go over more challenging, more difficult problems. So be sure to check that out once I post it. But for now, these are just basic problems to help you with your understanding. So yeah, let's take a look at this first one. A person walks 4 meters north and 4 meters east. What is the distance and displacement? Okay, so let's just illustrate this. The main point of this question is just to like highlight the difference between distance and displacement, which I'll show. So if we look at it, we're going 4 meters north. This is north, and then we're going 7 meters east. So 7 meters. So now the distance, as we mentioned when we're going over the terms, is just the total path length. So if we're going 4 meters up and 7 meters to the right, the distance would just be 7 plus 4 meters, which is just equal to 11 meters. This is your distance. Okay. Now here's what I'll get to. Let's find the displacement now. So the displacement is the distance from the final point and the initial point. So in this question, our initial point was here, starting right here, and then our final point we ended right here. So we want to find a distance from here to here, which is this length right here. So we want to find out the magnitude of this vector. So how we do that is if we have it going north here 4 meters and it's going east, the angle created here is 90. It's going directly from up to right, north to east. It creates a 90-degree angle. So now we can just use the Pythagoras theorem. And if you don't know what the Pythagoras theorem is, it's the square of one component plus the square of the other component, and the square root of that gets you the magnitude of your hypotenuse. This length, the greatest length side is known as the hypotenuse. So it would be like this. So let's just label this component x. So x would equal the square root of 4 squared plus 7 squared. And if we plug this into our calculator, which I am doing right now, we should get a value of 4 squared plus 7 squared. We should get a value of 8.062 meters. Well, rounded, of course. We'll just round to 8.06. That's a decimal meters. So this value here is your displacement. Your displacement. I'll just type it because it's easier. This value here. And yeah, this first question is done now. So let's move on to another question. Okay, let's take a look at this question now. A person runs a full lap in 13 seconds around a circle with a radius of 5 meters. What is the distance, displacement, average speed, average velocity by the end of the lap? Okay, so let's start with the distance. So let's first draw a diagram. Brushes. Okay, so the guy runs around a circular track. Does not get circle, but just go with it. And it's 5 meters is the radius. So that's the radius. So if we were to find a distance, that would be the total path length around the whole circle. Otherwise, and that's also just the circumference of the circle. So if we want to find the distance, which we'll represent by d, that will just equal the circumference, which is equal to 2 pi r, and since r equals 5 meters, then it's just 2 times pi times 5, and this equals, let me put it in the calculator, this equals 31.42 meters rounded. So that's our displacement. And now let's do the not displacement, distance. And now let's take a look at our displacement. So for displacement, like I said previously, you want to look at the starting point and the finishing point and find the distance between that. So when the guy starts running, his initial point is right, let's just say right here, but he does one full lap. So that means his final point would also be here. It would also be at the same place. Therefore, his initial point and starting point are the same. So the displacement is simply just going to be 0. Let me write it. It's just going to be equal to 0 meters. Okay, now let's do the average speed. So the formula for average speed is distance over time. So let's write that out. So speed s equals d over t. So distance over time, and we determined that our distance previously from solving this is 31.42 meters, and our time, it says it right here, 13 seconds. So our speed is equal to 31.42 meters over 13 seconds, 13s, and if we just plug this into a calculator, we should get 0.42 divided by 13. We should get 2.42 rounded. So 2.42 meters per second rounded. And this is our speed. Let's just label it there. Okay, I'll label this distance as well. Oh. Okay, now lastly, let's find the average velocity. So as we determine with our terms and stuff, the formula for average velocity is displacement. I'll represent that as delta x over time. So it's displacement over time. However, if we look here, we initially solved that our displacement is 0 meters, right? So if we substitute this in for 0, we get 0 over t, and that's just equal to 0 meters per second. So that's our average velocity. So keep in mind, if your displacement is 0, your average velocity is 0. And if your speed is, and also just like this is just to show that your average velocity can differ from average speed. They're not necessarily the same every time. So yeah, now let's move on to another question. Okay, a car driving 10 meters per second north makes a right turn and now travels 8 meters per second east. If the turn lasted for 2 seconds, what was the magnitude of acceleration of the car during the turn? Okay, so what I want to show with this question is that the x and y direction, they act independently of each other. They'll have independent velocities, independent accelerations, and independent displacements. So with this question, right, a common mistake that people make is sometimes they'll use the equation VF they use the equation VF minus VI over t to solve for their acceleration. However, they'll plug in the wrong values. Since they see that 10 meters per second was the starting velocity and then it goes to 8 meters per second, they'll do 8 minus 10 over 2 seconds to get -1 meters per second squared. Okay, but this is wrong because the 8 meters per second east and the 10 meters per second north, they're not in the same direction. One is in the north and one is in the east, right? So when they're in different directions, you can't solve for their you can't put them in the same equation. They'll have different accelerations and different velocities. So you have to solve for them independently, and then those in the north direction, whatever acceleration you get, that's the component. That's a vertical component, and whatever you get in the east direction, that'll be your horizontal component. And then we'll use a Pythagoras theorem to find the hypotenuse or the magnitude of the two components. So let's see how that will be done. So I'm going to delete this just to make room. And we'll first start with the north direction. So north. Okay, so the acceleration in the north direction I'll represent as VFN minus VIN over T. So if we look, our initial velocity, it's obviously 10 meters per second because that's what it was initially going. But after 2 seconds, so let's just draw it. It's initially going 10 meters per second. But then after 2 seconds, at t equals 2, here I'll make that t better. At t equals 2, right? It's completely going in the east direction, horizontal. So that means that the component in the north direction, the velocity in the north direction, has to be 0 meters per second because it's not even going in the north direction, right? So that means after 2 seconds, the final velocity in the north direction is 0 meters per second. So now we can plug in our values. So we have 0 minus the initial velocity of 10 meters per second divided by the time of the turn, which is 2 seconds. And that equals -5 meters per second squared. Keep in mind that the units for acceleration, they're always meters per second squared. And for velocity, they're meters per second. Time, there's just seconds. And displacement and distance, they're meters. That's the standard unit used for physics. Okay, so now let's look at the east direction. Here I'll erase some of this to make some room. So, okay, east. So now we're going to do like a similar concept that we did before. So initially, it's only traveling 10 meters per second in the north direction. So 10 meters per second north. So that would have to mean that in the horizontal direction, the right direction, or the east direction, this direction, it has to have a velocity of 0 meters per second, since it's not even traveling in that direction. So that means our initial velocity in the east direction is 0 meters per second. And our final is, nope, our final velocity is just 8 meters per second. So 8 meters per second. Okay, there we go. And our time is just the same, 2 seconds, right? So we can now plug this all in. So A in the east direction equals 8 minus 0 over 2, which is just equal to 4 meters per second squared. So now we found our component in the north direction and the east direction. So now what we're going to do is find the hypotenuse, or the magnitude of the two vector components. So I'm just gonna erase all this just to like show it, and boom, it's gone. So in the north direction, we had -5 meters per second squared. And then in the east direction, we had an acceleration of 4 meters per second squared. So now what we're trying to do is find the magnitude of this component that goes this way. So we can bring this here, so right here can become 4 meters per second squared, and I'll just erase it to make it look simpler. I'll erase all this. So now how do we find the length of this? We'll just use the Pythagoras theorem. So I'll just represent this as a, just regular a. So a equals the square root of -5 squared plus 4 squared. And if we just like plug this into a calculator or do it mentally, however you want to do it, we should get, one sec, we should get 6.4 meters per second squared as the answer. So this is our answer. 6.4 meters per second squared. Okay, let's move on to a projectile motion question now, and this will be our last question. Okay, this question says, a person throws a ball with an initial velocity of 30 meters per second at 40 degrees from the ground. How far is the ball from the person when it reaches the ground? Okay, so let's just show the vectors. So let's just say this is the ground, and the ball is launched at this velocity of 30 at a 40-degree angle. 40-degree angle. And basically when it says how far the ball from the person is when it reaches the ground, that's basically asking you to find the horizontal distance. Let's just say this is the horizontal distance. The horizontal distance, x, that the ball reaches when it touches the ground here. And somewhere here, right? Right here. So yeah, so in order to do this, we need to first find the time. So if we take the horizontal component, so if we find the horizontal distance, remember how we said that we neglect air resistance? So that means velocity is constant. So Vt, so Vit in the x direction plus 1/2 at squared. This portion cancels out, so our delta x is simply just equal to Vit, right? But we have no sense of displacement and no sense of time, so we can use the horizontal equation. So we can actually use the vertical displacement equation to find the time, because we're given acceleration, and we can find the vertical component by breaking into its vectors. So if we need to find the vertical component, we can break it into its vectors. So 30 sine 40 is 19.28. So Vy equal to 19.28. And this is also V sine theta. V sine 40, right? So now when the ball is launched, right, it goes to its trajectory, hits its max height, and then reaches the ground. Let's just say it reaches the ground here. So the displacement, the vertical displacement, it's gonna be 0 because it starts at the ground here and it reaches the ground. So if we measure the displacement vertically, we get 0. So now we can use the displacement equation. So delta y equals 0. So displacement 0 equals v I y t plus 1/2 a t squared. And since it's in free fall, our acceleration, our a is just equal to g, which is equal to negative 9.8 meters per second squared. So meters per second squared. So before we plug in any values, let's just like manipulate this equation to make it easier. So we can bring this viy t on the left side since it's 0. So negative viy t equals 1/2, and I'll just put in g for a, g t squared. And the t can cancel out. One of the t's here, so we can cancel this, and we lose the squared here. So we get negative viy equals 1/2 gt. And now we just plug in our values. So our viy, our initial velocity value we found was 19.28. So I'll make some room first. I'll just move this. So negative 19.28 equals 1/2 times negative 9.8 times t. So now we can just solve for t. 1/2 times negative 9.8. That is negative 4.9. So we can just do, if we just go over here, we can do t equals negative 19.28 divided by negative 4.9, and we should get an answer of, let me plug into a calculator. We should get an answer of, I'm gonna write it here, t equals just 3.93 rounded about seconds. So this is the time it takes for the ball to be launched and hit the ground. So now with this information, we can find the horizontal distance or displacement. And keep in mind, this question, distance and displacement are the same thing for the horizontal direction, because horizontally it's traveling, it's only traveling this way, and the final point here is the same as the distance traveled. So yeah, it's the same. Let me erase this to free up some space. Erase this. So we have our time, t equals 3.93 seconds. So now with this, we found that our horizontal distance or displacement is equal to VIT. I should specify that we have to use horizontal velocity since the vertical and horizontal are independent of each other. So now we have to first find what the initial velocity in the x direction was. So we do 30. So we have to find this value here. So we do 30 cosine x, cosine theta, I mean, which is 40 degrees. So 30 cos 40 equals, so that should equal 22.98. So 22.98 meters per second. And now, since we have our horizontal velocity, we have our time, we can find our horizontal distance. So delta x equals 22.98 times 3.93, and we should get delta x equals 90.31 or 32 rounded meters. So that's our horizontal distance. And what I want you to take away from this question is that when you have 2D projectile motion, you can use the y displacement to find the time, and then use that time you find to solve for the x distance. This will be like a common thing for lots of questions. And also, they're like, since the ball gets launched and lands at the same place, there are different shortcuts you can use. So as we established in the slides earlier, so the initial velocity the ball launches with will be equal to the final velocity the ball lands with. So you could also have just used the what's it called, acceleration equation. So I'll show that right now. Let me erase all this. Okay, so I'll show how you could use the acceleration equation. So we know that a equals vf minus vi over t, and if we just order this equation in terms of vf, we can get vf equals vi plus at. So we could have found the time using this equation. So we know that the vertical acceleration is just negative 9.8, and we know that the initial vertical velocity was 19.28. And since it gets released and lands at the same vertical displacement, we know that the initial and final velocities will be the same. Except that, like, since it's traveling in a downwards path as it's landing on the ground, the final velocity will be negative. So negative 19.28 equals 19.28 plus negative 9.8 t. So then we get 19.28 plus 19.28, or negative 19.28 minus 19.28, and that is negative 38.56 equals negative 9.8 t. And now if we divide by negative 9.8 on both sides, divide by negative 9.8 on both sides like this, we get that t is equal to 3.9 t, 3.93, like we have gotten in our previous answer. And then we can just do the same process from there, plug this into the delta x equals vixt equation as we found here, and then we'll get the same answer. So yeah, those are some shortcuts you can use if the ball is released from the same position and drops to the same vertical position. So if it's released from the ground and drops to the ground, you can use these shortcuts. And something else that you can note is that at the trajectory here, at the peak here, the time equals 1/2 of the full time the ball takes to travel its trajectory, t full. So at the highest point here, the ball would have a time of 1.965 to reach here. 65, because simply 3.93 divided by 2 to get the time here. And you can use this information by saying that at the top the vertical velocity, final velocity, is 0 at the top here, So we could have used this equation. So 0 equals VI, which is 19.28, minus 9.8 T. You could have found the time halfway, which would have become T equals 1.965. And you could just multiply this times 2, so you know the time for the full trajectory to happen, for the ball to like land, times 2 would have just gotten you this value right here. And then you could have plugged this time into T here, and then multiplied it times the horizontal velocity we found in the x direction, which was 30 cos 40. Yeah, these are just some shortcuts you could have used for this question. And that basically wraps it up. Thank you for watching this. I'll be posting another video on doing more harder, more challenging kinematic questions. And I'll also be posting more units like forces, Newton's law, circular motion, all those units. So be sure to check those out if you enjoyed this. And please feel free to email me if you have any concerns or questions. And if you're like struggling with any question that like by yourself that like I haven't taught or anything, you can still reach out to me and I'll do my best to reach out to you and help you with any questions you have. Yeah, thank you so much for watching.